Second part of lecture 4, we continue from burst, and now we are going to have a quick look at, well, not quick, we're going to look into the formulas of collapse. As I told you, there's a split between, well, how to word that? The pitch part is split into plastic and transition collapse, and the mathematical formulas how to calculate this. Basically, quite simple. You guys could do that yourself for any pipe. The limits and so on, they are listed down in the table below here. What you do typically is that you put in these values for F1 through F, is it up to 4? And then and these are predefined. And you'll find the DT criteria, and the DT criteria is what is listed here. Okay, so if you come out with a yield strength and this F, and these are the empirical parts that the API testing in the 1960s came up with. You'll find which category your pipe fits into. Let's see here. Yeah. For elastic collapse, the formula is a fixed constant, the D over T ratio multiplied with D over T minus 1 squared. So that's basically no, sorry, I am not saying the right thing right now. That's actually how you calculate the collapse itself and the collapse limit for elastic collapse. So once you have decided that, okay, my pipe, let's say that it's an H40, it has a D over T ratio above 43. Then it falls into category elastic collapse, and you can use this formula to find your collapse pressure. Yeah. For a transition collapse, you see yield strength goes into the calculation. The same with the plastic collapse. And for yield strength collapse, this is the formula. Basically, it can be derived back to von Mises. That's why that formula and that part of the collapse theory, API collapse calculations are quite accurate. The same with the elastic collapse.
For the yield strength collapse, you don't have limit as well?
Here, the yield strength goes into it. What do you mean limit?
Because you see that, I mean, from your table you have limit from
Here.
Yes.
Yes, yield strength is here. So if the DT goes above a certain value, then you switch over to plastic collapse or transition or elastic, right? So it has to be lower. For H, if it was an H40, it has to be less than 16. Yeah. Now, what the old professor taught me when I was learning this at this very institute, he said that if it's a value of, say, 15 or 15.5, in this case, calculate yield strength and calculate plastic collapse and use the lesser value, he said. So I can do nothing but to bring on that advice. That's how you do when you calculate it. Normally we never do. When you leave this school, you will not hand calculate collapse again, right? You just have to understand what is behind the software, and you know that this is what it does, right? kind of dangerous, isn't it? You have a black box thing. You feed it a lot of data, and out comes some curves. You know that this is what is supposed to go on the inside of that black box, and it just doesn't. Does it really calculate it correct, or is this factor changed a little bit? You never know, right? So what I'm arriving at is again what my old professor said: be careful with software models always. And there's not one software model that is 100% accurate. Never, doesn't happen. Yeah, we're switching over to actual. These F factors, I don't know if they are listed somewhere here. Even let me see if I can find. Are they not listed? They are not listed here. We'll this F1 through F4. Uh, they have specific ways of calculating them. It seems like they are not in this presentation, and that's a little bit sad. I will find them for you and present them for you at some point. Yeah, actual stress is very straightforward. It's the area and the stress, and you have a force. That's basically how simple it is. And the yield strength. Put in the geometry for the cross-sectional area, and you arrive at what is the tension limit. Now it's getting a little bit more interesting. Um, this is the yield strength, and with this one we could actually talk more or less a full class. I'll try to limit it very, very quickly. The blue area is what we call the acceptable design area. The red, big or fat oval is the von Mises. It's called triaxial stress. What is a little bit weird is that theoretically, and you'll see, you will actually see this also in North D10, that they have made this mistake. I'm letting this mistake go on so I can mention it to you guys, so that you can apply your very fresh learning now. You see this curve here, going here. That's a physically impossible curve, more or less. Why? It has to stay within the von Mises, right? Von Mises is the pure yield strength, basically. Whereas no pipe performs better than this, right? You cannot go at a higher level than the yield strength, so it doesn't really apply. It should be within the von Mises theoretically. Two more things to say about. Well, maybe we should talk about quadrants first. I guess you guys know, that's why I just went on with it. But let me first say that quadrant one, here you have a combination of burst and axial tension. Horizontal here is the tension. In the center here, everything is it's it's one place in the pipe. It's called a neutral point. You don't have any actual stress, and you don't have any dominant burst or collapse forces. It's the neutral point in your pipe. Um, on this side, compression. On this side, burst would be dominant. In the lower half, collapse would be dominant. There are no situations, basically, except a point in a well where there's well, yeah, you may define it as a point that there are absolutely no external pressure or absolutely no internal pressure. Um, where I'm going now, Burst and Barlow, as much as the 1960 calculations, they are assuming no opposite pressure. So Barlow, it says this is what the pipe can take when there's no pressure on the outside. Did that give meaning? Um, say that there's air. You test your burst, test your pipe in air on this ground with no actual stress. Then you get the Barlow curve here on top. Theoretically, then it's only valid in this point, number one. Putting a line out here would be wrong mathematically, right? Because then it becomes triaxial, which Barlow never was tested for. So it's yet again another factor why ISO and API says be careful with this formula. And it's conservative. That's what it is. It's conservative. Yeah. We see a stapled line here that's supposed to tell you that okay, couplings are important in your design. It's both true and not true. If you have these old type couplings that are called BTC, and then there's another one also I can't remember from the top of my head. They are performing less than the pipe itself, whereas threads, premium threads, they will in most cases today perform better. Just check in the catalogs, and you'll find that yes, these pipes and couplings are now stronger than the pipe itself. Yeah. Basically, pipe mates up, and you have the steel on the outside from the coupling, right? So it's thicker. So that's why it's normally today performing better. Yeah. That's a blunt way of putting it. Quadrant number 2, compression and burst. Quadrant number 3, compression and collapse dominant. Very, very few pipes come into these categories. We rarely have compression or a high value compression, right? Tension, on the other hand, we have a lot of it because all pipes are hanging from the top. Either it's a drill pipe, it hangs from the top drive, or it hangs from the wellhead if it's a casing, right? So a lot of tension. The higher up in the pipe, closer to the surface you get. Yeah. And this bent part here is a correction that API does for the triaxial part. Otherwise, it will be only valid in this point where there's no actual stress whatsoever. But at some point, the industry saw that, we have these nice calculations, but still our pipes are collapsing. And then they realized that when pipes are in tension, and specifically a lot of it further up to close to wellhead or top drive, then it tends to find collapses there, and they realized we need to correct for tension. So that's where API tries to mitigate for the triaxial part. Now would be a good time to show you that calculation. Basically, it's a pre-calculation for all of these calculations except for the elastic. What it does, it takes your yield strength and give you a reduced yield strength based upon the actual stress. Yeah, there is a slide that must have fallen out with or two for that matter with the F factors and the correction of the yield factor. I'm not sure that it's too dramatic for you guys. Formulas are your strong side, definitely. Understanding these curves is why we are here today. Yeah. Line number 3, pure compression. Pipes are then supposed to fail in pure compression at that limit, or it would be couplings, for example. They fail here at pure compression, theoretically. Pure actual tension, couplings would fail here, or pipes for that matter. Seems like it's pipes here. Line number 6, that's where we have the correction of actual tension for collapse for the API collapse calculations. Number 5, that's where we have elastic collapse. Remember that elastic collapse does not correct for yield strength. It doesn't look at strength whatsoever. It buckles, right? So that's why, and this you'll never see in any standard or at least Norsok D10 has a figure like this. They don't show conductor pipe with a straight line here or stapled or anything like that. It shows you this curve and the yield. And again, I would not see that von Mises should be on the inside of it. That would not be correct. Yeah, we talked about Barlow being actually valid only in this point, and they have put Barlow to this point because it has zero actual stress. It then should also be the same as the yield of von Mises, where von Mises has no actual stress, or none of these components, and it's a pure internal stress. They should convert towards each other. Design factors. You guys have been talking about design factors before. You have in your classes, so I'm just going to show them to you, not say what they are. We have typically different design factors for casing, tubing, and tubing in service, tubing testing while testing it, pressure testing, for example. Yeah. So different design factors for different stresses: burst, pure tension, compression, collapse, and triaxial. Yeah, safety factor is a complete different matter. And what we do very often, we reduce. You'll see von Mises, if you play around with it, you'll see if you change the design factor, you'll see that the von Mises shrinks. That's what you see in your software. A little bit historical facts. 1678, Hooke's law. You guys are familiar with it. It's the linear part of steel. Euler, with his column theory, 1744. Cauchy, he came up with a stress tensor. That's how we know stresses in steel and how steel fails. Barlow, he came in 1836. More circles and failure theory, 1852. Gabriel Lamé, he was in 1852. He gave us elastic stress in tubes, and and our principal stresses. St. Valence principle, that's basically showing how stress goes into steel, Tresca failure criterion, and then finally what we are using today, the maximum distortion energy criterion. Basically, it's only triaxial, everything. All modern calculations, only triaxial, nothing else. Yeah, and even if we got von Mises in 1913 for the first time ever, the ellipsis is actually another guy, Heinrich Henke. He made that ellipsis for the first time in 1924, and something called hydrostatic pressure that came and we started discussions around that. It's kind of a little bit out of the scope of this class. Pipe properties. Let me now ask for questions. Do you want to repeat anything? Anything unclear? Everything unclear? This part is basically not extremely straightforward and easy to understand. You need to absorb it and work with it, and then it will mature for you guys. Pipe performance. This is a collapse curve. How modern pipes perform. Just to show you a little bit why we are using modern calculation techniques sometimes. This is a curve that I got from a pipe manufacturer. They're saying, and I forgot to tell you, the API test based upon how pipes were performing in the 1960s, they call that method for minimum performance. Those pipes that they collapsed, they are supposed to represent any pipe produced by anybody. And what they did, they added to the to the um, to the math behind the different categories of calculations a certain safety factor that is built into those calculations to accommodate that and make it what is called a minimum performance standard. On top of that, we are using the design factors that we just saw, right? So the picture becomes like this. The 0. The 12.5% wall loss that is acceptable in manufacturing, that still is the API standard. Like I said, it's no longer very often you'll find somebody producing pipe like that. They are producing something else. And that has a much more accurate wall thickness. And this manufacturer says, based upon full-scale tests, our minimum performance is this orange curve. Now, if you plot the API performance from 1960, it's the black curve below. So that's how the minimum performance with a certain baked-in safety factor would perform, right? And then the blue line is the design factor that you do. If you calculate and see the difference, you lose quite a significant portion of your collapse strength if you use the old type calculations, or call it the industry factor. So it's again a Volkswagen Beetle. It can take anything, yeah, and it makes sense what the industry is doing for some areas. For example, offshore fields where you drill from a platform. because if you get a little bit more casing wear than what you planned for, you need a little bit of extra leverage, a little bit of extra wall thickness. Yeah, go ahead.
Is there any test like this numbers on casing with recorded here?
Yes. Thank you for the question. To be honest, when I did my PhD, there was another magnificent, brilliant student called Andreas Tegland. He developed what is the most accurate calculations for collapsed worn pipes, calibrated for over 30 physical. Yeah, I think it's 30. Or if you, there's a number 60 spinning in my head, but I think it's 30. It's in a paper available. There used to be a calculation from a guy called Kuriyama. He was the most accurate and the only thing that existed in the industry, quite accurate. But the new calculation technique based upon the work of Andreas Tegland is the most accurate in the industry, and it's not commercially available. We made we did it as a team, me not being more than a guide. um, and have some input, but that model was proven with a variety of pipes and the collapse tests with different types of wear, and it's very accurate. Yeah. So yeah, good question, and we're very proud of that model, but it's not used for anything right now. So if anybody is really good at programming, there's a really good business idea there. Yeah. Yeah, so that's how pipes, and the truth is you lose up to 40% of your strength in this calculation if you say that uh, my pipe can't take more than this. In this area here, you see when you come close to yield strength collapse, there's no difference, right? Because it's mathematically derived from yield, which is accurate. And basically it's the same when you go over to elastic collapse, mathematically derived, more or less no difference. All right. When it comes to the pipe properties, we remember. Yeah, go ahead. Yeah. Yeah.
I mean, when you have the transport, normally the collapse resistance is higher.
The collapse resistance is higher, but when you,
I mean,
this is your design
like
limit.
less than full scale gas in non-performance. I think normally the collapse resistance.
If you go to this stress level up here, that's where it collapses. This has a built-in safety factor. So if you go to this level, it doesn't collapse. It is the minimum performance. So it means that any pipe manufactured should tolerate this with this DT value 18 should endure this collapse stress, right? So you design your maximum. Uh, you design so that the maximum stress, collapse stress that this pipe is enduring doesn't exceed this blue line. That's how you do it. Design factor reduces the level that you allow your pipes to be exposed to. You reduces the allowable area, allowable level. Sorry. You say that my pipe should not be exposed to more than this. And then you know that this is the limit, that it starts to collapse after this, where in fact that value is actually up here. Yeah, we talked about the manufacturing process, and if you read a little bit in the literature, you'll know that a lot happened in the 70s and into the 80s when these processes were computerized. And one thing that is very cool, when they calculate rupture now, they are so accurate. And if there's flaws in the pipe, then this is revealed through the rupture point of pipes. And they are so good now with the inert gases and computerized processes, so pipe performs in a much better way. That's why we see this gap from the 1960s. It's just the manufacturing process that is so much better. When it comes to burst, if you do the correct calculations, and you consider that actually burst in a burst situation, and you forget about that simplified way of there is no internal pressure, because that's another problem with the Barlow formula. And many of those calculations, they are based upon pure outer pressure and nothing on the inside. Also with the API formulas for collapse, there can be no internal pressure. It becomes inaccurate because the surface area also is different on the inside and the outside of the pipe. In 2015, they came up with some addendum to the standards, and they changed the formula slightly, but it's not 100% accurate. When it comes to burst, we again made a new formula at NTNU for accurate burst calculations, triaxial burst. That's actually a master thesis here, made by two excellent, brilliant students. They used Lubinsky formula, and that's very simple, really. Theoretically and bluntly, you have the von Mises and you have Lamé, and you put them together and you get triaxial burst. And that's the formula here. And what happens when you start to apply different outer formula, outer pressure, the von Mises starts to move around. You see it here. If you have zero outer pressure, you have the green curve, and the red one is for a situation where the collapse pressure is 10,000 psi, but still burst will be the dominant, if you see what I mean. Yeah. So these are things that does not go into any modeling software in the industry at all. And again, another very, very important academic calculation and model. Again, not commercially available. Very, very good business idea, I guess, sitting in a drawer here at NTNU. Yeah. And you can burst this very straightforward when it comes to wear, accommodate wear. It's just to reduce the wall thickness, and you have it's proportional. Only one other thing, yeah. When it comes to burst and Mr. Barlow and these calculations, what API has been recommended for years, and what you will hear everywhere is yeah. Go ahead.
Something else that I was just wondering if there's any equation that takes time into consideration, because there must be a difference if you load this, if it's loaded in a matter of seconds or in a couple of hours, how the material behaves. I would imagine if you load something immediately, or you are doing a test where you're building up the pressure slowly, that it will behave differently, and it will be stronger in one scenario versus the other. Since
No, you're correct. But we are talking then about fatigue. Fatigue would be the thing. Um, why it would be fatigue, and not what you presumed or were speculating on, because exactly what your fellow student in front of you asked for. I was going to talk about this part. Let me quickly go to this curve again then. Because this curve, as I tried to explain it, and how I corrected it on the question, see what this does. Remember that on burst, on burst side of things, you go to yield. Yield is the point where you have 0.2% permanent deformation, right? Yep. And now we say that, just as an exercise, because this is collapse, and these pipes are not having a pure yield. They also have this geometrical part, right? But if you think about this picture as a purely loads to yield question, this is the point where you start to yield, right? And below here is the stress that you allow your pipe to be exposed to. So you never go out of the linear area. Let's go to another drawing. Here. Take away. Here. You never load higher than, say, in this range here. So when you offload, you go down again. And if you go up fast or slow, it doesn't matter. But it is correct still what you're saying, because you will have, remember what we had in the first session with the material science, that the atoms are in a lattice, right? And there are failures in these lattices. Every time you load them, something will happen at a microscopic level. Yeah. So we have fatigue, and I'll tell you something else interesting for those who were there. Remember, there's FCC and BCC. The BCC structured steels, they have fatigue. FCC do not. FCC structured metals, they do not have fatigue. For example, aluminum don't fatigue at all. I cannot explain why, but that's how it is. And it's interesting, right? For example, you'll find that any structure in a plane is aluminum because it doesn't fatigue. Yeah. So yeah. But at the sub even below yield, you will experience fatigue actually. So you load it enough times, and something will break. Did I answer your question?
yeah, more or less.
Yeah. If yeah, I hope so. If not, ask again in a way so I understand it better. And yeah, yeah. So we talked about burst, and we went here, and yeah, I was on the point of saying something about burst. Yes, that's kind of important for you guys to know, I guess. Um, um, the literature is full of this thing called the highest stress is always on the inner diameter of the pipe, on the inner wall. It's absolutely true. And that's where they put their design criteria. So, for example, burst here listed and everything else everywhere in the industry that says that, yeah, we set yield at the inner wall of the pipe. Now, if you compare that to any other structure in the world, a bridge, how you put it up, design wise, yeah, the undercarriage of a plane, whatever, it doesn't work. And it is also another safety factor that is built into burst. Okay, so the pipe will not deform if, let's say that this is the wall thickness of the pipe and this is the inside of the wall, trying to make a curve here for the outer wall. Okay, so the stress, you have to increase the stress level so that the level of yield goes all the way through your wall and hits the outside. At that point in time you will reach permanent yield, or deformation and yield, 0.2% yield. So that's another safety factor that is built into the industry burst calculations. Yeah. And of course, at the NTNU model, that is the case. It's called through wall yield. And every now and again, you'll see that this mentioned as a calculation and predefined, yeah, in the literature, you'll see that a few are talking about, a few ones are talking about through wall yield. Yeah. Design regulations. Yeah, I'm not sure I want to talk about this. For one thing, we are, yeah, we are at the end of. Yeah. So let's basically just say that there are two standards that we are going to look into. The one called 5CT is basically the ones for how you manufacture your pipe. And I've been talking about the API collapse and burst calculations. They are in API 5C3 and ISO TR 10400. Yeah. So these are the two standards that we will talk a little bit about and that you will be using as drilling engineers or build upon. Yeah. Yeah, and there's something about casing we are coming up here also, I see. That's about it. We will have a standard lecture to talk about these things on Thursday. And by then I will have access and I will be able to set up the exercise in the basement. And yeah, I hope that you guys can put up some expectations, some just feedback to me what you want to talk more about, less about, repeat, whatever. Yeah, and again, the recordings will be uploaded and made available for you guys. I will send out today's lecture, and I will give you all of my remaining slides on the emails that I have. Yeah, in addition to what was covered. Everybody has a copy of that old compendium that is about 80-90% finished. Yeah, very good. All right. Questions before we say call it a day? There is actually one thing I come to think about, the theoretical exercise. Not the full class here today, but I think I will send out the exercise so that you guys can have a look tonight and tomorrow and prepare a few questions for me on Thursday. I will try to make myself a little bit available after the class so that you guys have that exercise going for yourself. Ask the questions that you can. I don't know if there's any student assistants in this class yet. Yeah.
Yes, I have a question. Sometimes it's like, I mean, my site is most of the time confusing. It's like maybe you're in operation and maybe it can be the tubing string or maybe the casing you're using from one company.
Yeah.
You have to you have some equipment that you
Use again.
yes, you have to use again maybe for another campaign.
Yeah.
And maybe they have lose the thickness.
Yeah.
But I mean, if the equipment, I mean, the string that you lose the thickness, and it still meet the requirement from the von Mises, it is always safe to use them. Like
Yeah.
maybe it can be maybe from class 2 or class 1.
Yeah. Okay.
Is it really safe
Yeah.
to use
Yeah.
these two again, even if
Absolutely.
maybe the
Yes, no problem.
yes.
I'll answer this because basically I've been using pipes again um, in a specific land-based field. They used to have what is called a storm choke, and then it was decided to change over to downhole safety valves, which is kind of a more easy. Yeah, it doesn't matter. The tubing costs a lot of money, and we saved a fortune reusing the chrome pipe. They are you won't believe what it costs. It costs a car per joint. Maybe not a new one and a very good one, but it is you'll get a car even in Norway for one piece of joint. Yeah, chromium pipes. So what did we do? We hired an inspection company. We laid out all the pipe that we recovered. We inspected the threads, of course. They are important. And we did the wall thickness measurements. All right? Yeah. So you can do this for tubing. For casing, you can more or less forget about it. Why? Because it's going to be stuck. You'll never get the casing out, and it will be so much force put on it the absolute majority of cases. You will have to use so much force to get to free it that the threads would be questionable. Corrosion wise, it would be questionable. Yeah, a lot of things. So, but the tubing you can reuse it. And again, what you learned today basically is the 0. I'm going to use 12.5% wall thickness, right? And the old API calculations, and I always call them the Volkswagen Beetle. It's saving you again, right? Using the old type calculations and this hidden safety factors everywhere, right? So you measure that. Okay, my wall thickness is still within theoretical loss is less than 12.5%. And remember what I said, modern manufacturing is 0.5% or better, right? Wall thickness loss when you produce it. Because let's face it, the OD is always the same. Always. Why? If it's larger, you can't fit it through your well, you can't get it down, right? So see, the OD has to be always the same. Where you have a variation is on the inside, the wall thickness, right? And basically that's what we did. The inspection company measured a minimum set of wall thickness. They actually scanned the full joint, and that was saving us a fortune. Yeah, that was a campaign of many wells that we reused the tubing. And once you know that it's less than 12.5% wall loss, all your calculations are valid. And of course, you can't over torque the threads, right? The threads has to break at a certain torque. Otherwise, yeah, you have to rethread the pipe.
So even if you lost more than 20% of the thickness, you can still use it.
No, then you can't. The limit of wall loss is 12.5%, right? Otherwise, you're in a different scenario. You can't use these calculations anymore. Then you have to go to special calculations that consider wall loss. And theoretically, they do some of these ones, but that's not what we did. We didn't do that. We said 12.5%. If there's more, scrap the pipe. And basically, it wasn't, right? Because yeah, let's face it, 5% is the normal reduction. And that's quite
because most of companies they only want to reuse the stream.
Yeah.
They only want to
Yeah.
reuse the stream.
Yes, they do. Yeah. Yeah, except for subsea wells, you don't reuse pipes. Why? Because the failure, you don't know if the failure percentage is higher, right? And to do intervention, you haven't saved anything because it costs so much with the rigs and everything else, right? So that's subsea. You don't reuse the tubing, as I've never heard about that. But in land-based operations, yeah, you do. You can.
Yeah.
Thank you, guys. See you on Thursday.